Hello all. I'm very happy that I'm gonna be going over paper 3, okay? And this is for the UK Edexcel curriculum, okay? And this is the first paper 3 I'm going through, okay, in this channel. And it's from June 2025, okay? And I recently uploaded paper 1 from 2025 and paper 2 from 2025. And as I said, one of you emailed me requesting actually papers 2 and 3 from 2025. So with this video, we complete the papers taken last year pretty much. Okay, so hopefully this is useful. For those of you who are taking the international Edexcel, okay, this paper is something like a combination of Unit 3 and Unit 6. Okay, so it's really useful for those who are taking Unit 3 and Unit 6 as well, okay, from what I saw. And I don't think I have anything else to say at this point, so let's dive in with question 1. A student investigated the variation of current with applied potential difference for a filament lamp. This is the filament lamp. Under normal working conditions, the potential difference across the bulb is 3 volts. The circuit diagram shows the circuit the student used. Comment on the suitability of the student's circuit. Okay, so as you can see, the ammeter is in series with the bulb and the variable resistor. The voltmeter is in parallel with the bulb, so that's good. But the potential difference is 9 volts, and they say that the filament lamp takes up to 3 volts, okay? So this might create a problem depending on the value of the variable resistor, okay? So, I mean, I'm trying to say that more than 3 volts might be applied across the bulb, which is not good. It's probably gonna burn, okay? So let's write this down. So the ammeter is in series with the potential difference and the light bulb, okay, and that's good. The voltmeter is in parallel with the bulb, with the bulb. And finally, the potential difference is 9 volts. So it so if the variable resistor is too small, we could get a PD larger than 3 volts across the light bulb. Okay, and that's not good, obviously. And I'm sorry. And I think this is a good answer. So let's move on. When the potential difference across the bulb was 3 volts, the student recorded a value of 1.29 amps for the current. In his conclusion, he stated this will give an accurate value for the working resistance as the value of current is precise. Assess the validity of the student's statement. You do not need to carry out a calculation. Okay, so first of all, let me think. We have to define what accurate and what precise means. Okay, so precision means repeatability. Oops, excuse me for my really horrible handwriting. So precision means repeatability, okay, and consistency. Okay, a precise measurement is one that would give similar results if repeated. With one measurement, the 1.29 amps, we cannot know whether repeated measurements will agree. Okay, and so we cannot know if measurement is precise. Okay, now about accuracy. Okay, I think I've written way more than I should for this question, but I just wanted you to understand what's going on. Okay, so excuse me for writing too many things. So accuracy now. So let's underline this with red. Okay, so now accuracy means how close we are to the true value. Okay, now here we do not know. Here we do not know, and I'm going to underline the accuracy, by the way. So this is a working definition. I mean, you can use it in other tests. So here we do not know the true value. The true value. So we cannot know. So we cannot know whether the measurement is accurate. Okay, and that's the answer. Let's move on to question 2. By the way, this was a really long test, and let's go back to the front of the paper. So for these papers, you have 2 hours and 30 minutes. Okay, again, this paper 3 from 2025, and this is from the UK curriculum. But from what I understood, this curriculum is also followed in international schools all over the world. So whoever is taking paper 3, I mean, this is what we are working at. So in all the videos I make of this sort, I say that usually, for example, let's go back to question 2. It awards 5 marks. So the rule of thumb is to use about a minute for each mark. So for question 2, it should take us 5 minutes, say something like that. Okay. All right. So question 2. A transmitter produces microwaves with a frequency of 10.7 gigahertz. The microwaves are directed towards a metal plate. A microwave receiver R, this one, okay, is placed between the transmitter and the metal plate as shown. Okay, when R is moved along the line AB, the intensity of microwaves received is observed to increase from minimum to maximum a number of times. The distance between successive minima is about 1.5 centimeters. Explaining these observations, your answer should include a calculation. Okay, so let's do some calculations first, and then we can write what's going on. So since F is 10.7 gigahertz, this is a 0. Okay, so 10.7, I'm sorry, 10.7, and then we're given delta x for minima to be 1.5 centimeters, but okay, we don't need it here. So what I'm trying to calculate now is the wavelength of these microwaves. So microwaves are electromagnetic radiation, which means that they travel with the speed of light. So since V is lambda f, then lambda is V over f, therefore C over f. the speed of light. So 3 times 10 to the 8 over 10.7 times 10 to the 9, since it's gigahertz. And with this calculation, we find the wavelength to be 0.028 meters or 2.8 centimeters. This is a very interesting wavelength, because notice that the distance between successive minima is 1.5 centimeters, which is about half of the wavelength. So this should ring a bell in your heads, meaning that, think about it and write in the comments, okay? And I will provide the answer, of course. So, okay, we found the wavelength. Now, the second step is to write what's going on. So I'm going to use a clean page. The waves are reflected by the metal plate, okay, and superposition occurs between the incident and reflected waves, okay. And this superposition creates a standing wave between where is it, A and B. A and okay, maxima occur when the path difference is an integer multiple of lambda, okay. So I mean, in a future test, they might ask something. I mean, they might give you the distance between two maxima, okay, in which case you will use lambda, okay. But in our case, we have minima, okay. So maxima occur when the path difference is an integer multiple of lambda, and minima when the path difference is an odd multiple of lambda over 2. So lambda over 2, 3 lambda over 2, okay, 5 lambda over 2, etc. Okay, so since lambda over 2 is 1.4 centimeters, which is about the same as 1.5 centimeters, right? Minima are observed every 1.5 centimeters. Okay, I mean, there is an error in the measurement and so on. So this is a complete description of what's going on in problem 2. Now let's move on to excuse me, to problem 3, which I have to admit that gave me some trouble until I was able to figure it out. So okay, let's see it. A student uses a digital balance. She sets the balance to 0 and then places a prism on the balance as shown. Okay. A uniformity rule. So in this situation, we have the weight of the prism and the reaction from the balance. Okay. And now in the second part, they say uniformity rule is pivoted at its 5 centimeters mark. So here, okay, the meter rule is then supported horizontally at the 30 centimeter mark by the prism as shown below. So this is the 30 centimeters mark, and this is the 5 centimeters mark. Okay, so this is what they mean. The meter rule is in equilibrium, meaning it doesn't rotate. Okay, explain why the increase in mass recorded by the balance is not equal to the mass of the meter rule. Okay, so the reason is because the ruler is not at the center of gravity. So the center of gravity will be, since this is a meter rule, it will be at the 50 centimeters. So 35, 40, 45, 50. So if the prism was there, we will get the real weight of the rule, but we don't. Okay, so let me demonstrate actually what's going on. I'm going to use a clean page. So let's go here. So let me show you. So this is the pivot, okay? It's a simplified version of the problem. Okay, so that's the pivot. This is the meter rule. And let's say that the prism is here. Okay. By the way, let me try something. If I do one move, okay, it creates a triangle. Okay, that's great. So if you draw it, in one stroke, it creates shapes, if that makes sense. So yeah, it's a new feature, or maybe it was a feature that was, it is a feature that was always there and I never discovered. So anyway, so if this is X, and this is the center of gravity of the ruler, okay, and this distance is Y, say, okay, we have two forces acting here on the ruler, right? The normal force from the prism and the weight that applies to the center of gravity. Okay, so to go back to the answer, I'm sorry that I take my time to answer, but I'm trying to explain what's going on. Okay, so the ruler is not, sorry, it's better to write the prism is not at the center of gravity of the ruler. Okay, now since the ruler is in equilibrium, in terms of the moments acting on it, comma, then n times x is equal to the weight of the ruler times y. Okay, so n is equal to the weight times the distance y over x. Okay, but since y is larger than x, then the normal force is actually larger than the weight. So the balance shows a weight higher than the weight of the ruler. Okay, and this is part question 3a part 1. Okay, now part 2, calculate the weight of the meter rule. You should take moments about the pivot. Okay, so first of all, we have to find n, the normal force. So finding, not Nemo, n. Okay, so n is, if we go here, we see that we have this indication, 180.2 grams when the meter rule is there, and 25.5 grams when the meter rule is not there. Okay, so n is 180.2 minus 25.5 times g, okay, and times 10 to the negative 3, because this is in grams, so it's 180.2 grams, so we have to convert to kilograms. So if we do this calculation, we find 1.52 newtons. Okay, so if we take moments now about the pivot, we will have n times x. Okay, I mean, I'm using the terminology we used earlier, where x is going to be 0.25 meters, and y is going to be 0.45 meters. Okay, because this is 0.05 meters, and this point over there is 0.3 meters, and this point there is 0.5 meters, so we have to subtract. Okay, so 0.3 minus 0.05 is 0.25, and 0.5 minus 0.05 is 0.45. I hope this makes sense. If it doesn't, ask me in the comments and I will explain it better. So n times x is w times y, so w is n times x over y. So 1.52 times 0.25 over 0.45 yields 0.84 newtons, which is the answer. Okay, I hope this makes sense. Part B, the student wants to reduce the percentage uncertainty in the value obtained for the weight of the meter rule. The student repeated her determination of the weight of the meter rule. She moved the prism towards the center of gravity of the meter rule before taking moments about the pivot. Deduce whether the percentage uncertainty in the value obtained for the weight of the meter rule is reduced by the student moving the prism. No calculations are required. So since the weight is proportional to the reaction force times x, comma, then moving the prism towards the center of gravity okay, will increase x, therefore reducing the percentage uncertainty. So this is the percentage uncertainty in x, which is equal to the absolute uncertainty in x over x times 100. Okay, now I need a clean page, but n will decrease. Okay, therefore the percentage uncertainty in the reaction force n, which is equal to the absolute uncertainty in the reaction force n over n times 100, will decrease. Will increase, I'm sorry. If n in the denominator decreases, then the percentage uncertainty increases. So this will increase. Thus, the percentage uncertainty in the weight, which is equal to the percentage uncertainty in x plus the percentage uncertainty in n, might increase or decrease. So we cannot reach a verdict, I'm sorry. So the student is wrong. Okay, so the student is wrong. Okay, this was I have to say it was, I think, a complicated problem. Okay, so it involved a little bit of thinking. So question 4, two students, A and B, used the cobalt-60 source to investigate the inverse square law for a gamma radiation source. Cobalt-60 is a pure gamma emitter. A, the cobalt-60 source was placed in a source holder. Okay, this is the source holder. All right. Okay, a Geiger-Müller tube was connected to a counter and placed a short distance D away. Student A set up the apparatus as shown, and student B used the same distance d but rotated the Geiger-Müller tube by 90 degrees as shown below. Both students recorded the count for 2 minutes. Deduce which setup will lead to a smaller percentage uncertainty in the count rate. Okay, first of all, if we set up the Geiger-Müller the way the student A put it, we will have this surface area exposed to radiation, so we will measure more counts. Whereas, actually, let me erase this, maybe it's not clean. So something like this. This is a surface area exposed to the radiation. But for student B, only this surface area is exposed to the radiation. So student B will get less radiation, so more uncertainty, okay? So let's write this down. So a larger surface area of the Geiger, of the, let's call it GM tube, okay, is exposed to radiation with the students A, with the students A, with students A, yeah, set up, okay. Thus, a larger count rate will be recorded, okay, for the same distance. And hence, the percentage uncertainty in the count rate, let's call it C, which is equal to the absolute uncertainty in the count rate over the number of counts times 100, will be smaller for student A. Okay, so student A is the best. I mean, his or her setup is better for this experiment. Okay, part 2, explain 2 modifications to the experimental method which would improve the accuracy of the data. So first one is to record for longer than 2 minutes. Okay, to increase counts. Okay, that's the first one. And the second one is to measure the background rate. Okay, so measure the background radiation and subtract from the measured radiation. Okay, question B. Student A suggests that the investigation into the inverse square law for a gamma radiation source could be carried out successfully using a radium-226 source. Radium-226 emits alpha and beta radiation as well as gamma radiation. Explain one modification that would be necessary if a radium-226 source were to be used. So we have to use an aluminum sheet between the source and the GM tube to block the beta and alpha particles. Alpha particles can be blocked with just paper, but beta particles do not. Are not blocked by paper. So we need aluminum foil to make sure that both alphas and betas are blocked and only gamma radiation goes through. All right. Question 5. Fused wire is made of a metal that has a low melting point. The wire melts when the current exceeds a maximum value. A student investigated how the cross-sectional area affected the current at which a wire melted. She used wires of the same length and metal but different diameters. The student steadily increased the current through each wire and recorded the maximum current through the wire before it melted. A. Describe how the student could determine an accurate value for the cross-sectional area of a wire. So use a micrometer and correct for zero error. Okay, measure the diameter at multiple orientations of the wire. Okay, and different positions. And calculate the mean. Okay, and then use A equals to pi d squared over 4 to calculate the area. Okay, B. Explain why a current in a wire causes the resistance of the wire to change. So current increases the temperature in the wire. Okay, so the amplitude of vibration of the lattice, the amplitude of vibration of the lattice ions, increases. Thus, electrons make more frequent collisions with lattice ions. So resistance increases. Okay, part 2. The length of a wire does not affect the value of current at which the wire melts. Explain why. Assume the wire behaves as a black body. Okay, so maybe the best way to demonstrate this is to use a clean page. So the wire, you can picture it as a cylinder, right? So something like this. And the surface area, so if this is the diameter d, which is equal to 2r, and this is the length, then the surface area of the wire is going to be equal to the circumference times L. So 2 pi r times L. How do we know this? Imagine cutting, I don't know, a Coca-Cola can, for example, like you take scissors and you cut it and then you unroll it. The surface area that is unraveled is equal to the circumference of the can times the height, right? So it's the same thing. So since d is 2 times r, we can also write this as pi dl. Okay, so this is the first step. Now, the power radiated, so P radiated can be taken from the Stefan-Boltzmann law. If you consider this to be a black body, it's going to be equal to the Stefan-Boltzmann constant times the area times times t to the fourth. So this is equal to sigma times pi d l t to the fourth. Okay. Now the heating power. So this is the, let's write as, let's write this. Okay, I'm sorry. So this is the radiated power. The heating power, P, is I squared times R, but R is given by the resistivity times the length over the area. Okay, the cross-sectional area of this wire. Okay, so notice that the power radiated away is proportional to L, and heating power is also proportional to L. So they increase by the same factor. Okay, but the melting point is at a fixed temperature. Thus, the current at which the wire melts does not depend on L. Okay, and this is because if you increase L, you increase both the radiated energy and the heating power, so it has no effect pretty much. Okay, all right, let's move on to question number 6. Air at room temperature was sealed in a closed container. The container was placed in an ice bath and the temperature of the air decreased. The volume of the container remained constant. Explain what happened to the pressure exerted by the air. In your response, you should refer to the momentum of the air molecules. Okay, so this is a long writing problem. You can see the asterisk there, which means long writing. It awards 6 marks. Therefore, it should take us about 6 minutes. But here I want to refer to something else that is related to the A-level tests in general. I mean, both the international and the UK ones, and so on and so forth. So 6 marks in long writing or writing problems means that you should provide about 6 arguments or 6 explanations for the question asked. Okay, so let's see a possible answer. So the temperature decreases, so the kinetic energy of the molecules decreases. And we can see this from the kinetic theory. So 1/2 m times the average speed squared is 3/2 kt. So if t decreases, v decreases. Okay. Okay, so the momentum then, the momentum of the molecules, which is P equals to mv, also decreases. Okay, the volume is constant, so the distance to the walls is the same, but the molecules move slower, and hence collide, and hence collide less frequently. Okay, let me use a clean page. Each collision thus yields a smaller change in momentum, okay. So the rate of change in momentum delta P over delta T decreases, but F, the force, is delta P over delta T, and pressure is force per area. So if F decreases, pressure decreases, and that's the answer, okay? So yeah, I mean, it's also another involved problem. I mean, this was a difficult test, I think, okay? I mean, compared to the other ones I've seen in Unit 3 and Unit 6 from the international test, I figured that in the UK curriculum, you take your practical test in the end, so in year 13 probably. So this is a much longer test and more difficult, I think, because it involves everything. So, I mean, everything from the AS and A levels, okay? Question 7, a student has 10 identical flat metal discs. One of the discs is shown. Each disc has a diameter D of about 5 centimeters and a thickness T of about 2 millimeters. All right. So this looks like a coin, by the way. I don't know why they call it a disc. So the student determined the density of the metal the discs are made from. She used the half-meter rule to measure D for one of the discs. She used vernier calipers to measure T for one of the discs. All right. The student then repeated this process for 2 more discs and calculated average values for D and T of the discs. Describe improvements to the student's method that will give more accurate values for D and T of the discs. So the first improvement is that, again, notice that this is a 4-mark problem. So we have to provide about 4 arguments. Okay, so instead of measuring the thickness of one disc, stack a number of discs, measure the thickness using the calipers, yeah, and take the average. So, I mean, stack them like this. So maybe you will have, here we have how many? 1, 2, 3, 4 discs. And use your calipers to measure the thickness. And this reduces the percentage uncertainty because the percentage uncertainty in the thickness is equal to the absolute uncertainty of the thickness over the total measured thickness. Okay, so you increase the thickness by stacking more disks, so that you reduce the percentage uncertainty. And you have to multiply by 100%. All right, clean page needed again. So, okay, and the other improvement is that instead of measuring D for one disk, you can lay disks next to each other, measure the total diameter, I guess, diameter and average. So you have to put them side by side like this, I guess. So 1, 2, 3, 4. And then you can measure the diameter of 4 disks. Again, this reduces the percentage uncertainty. Okay, so I mean, you have to divide by the number of disks in both cases, okay? So the percentage uncertainty here is going to be the absolute uncertainty for the diameter over the diameter. So if you have more, you reduce the percentage uncertainty. Okay. Right. Part B. The student determined the average mass of a disk to be 42.5 grams plus or minus 0.5 grams. Calculate the density of the material the disks are made from and the percentage uncertainty in this value, and they give you also the average diameter of a disk and the average thickness of a disk. All right, so density is mass per volume. So this is mass over the volume of a cylinder, pretty much. So pi times d squared over 4 is the cross-sectional, I mean the area, so this, the area, right, times the thickness gives you the volume of a cylinder, right? So we have 4 times 42.5 times 10 to the negative 3 kilograms over pi times d squared 5.2 times 10 to the negative 2 squared, and then we have meters squared, and then the thickness is 1.9 times 10 to the negative 3. Why did I cram everything there? Okay, I'm sorry, let's write this again because it's crammed in there. So this is mass over 4 pi d squared times t, which is equal to 42.5 times 10 to the negative 3, and this is kilograms, over pi times 5, and I forgot to multiply by 4, okay, 5.2 times 10 to the negative 2 squared, and then times 1.9 times 10 to the negative 3, and then we have meters cubed. So this yields 10,532.68 or 10,532.7 kilograms per cubic meter. We are not done. We also need to calculate the percentage uncertainty in this thing. Okay, and I will need another clean page. So let's start with the percentage uncertainty in the individual quantities measured. So the percentage uncertainty in the mass is equal to 0.5, which is the absolute uncertainty in the mass, over the mass itself, 42.5 times 100% yields 1.18%. The percentage uncertainty in the diameter is 0.1 over 5.2 times 100% yields 1.92%. And then the percentage uncertainty in the thickness is 0.1 over 1.9 times 100 yields 5.26%. Okay, now the percentage uncertainty in the density. I have a video talking about uncertainties, by the way. So when we divide things, we add the percentage uncertainties. And when we have a power, we multiply the percentage uncertainty by that power. Okay, so in other words, this is our formula, right? So we have to add the percentage uncertainty in M plus the percentage uncertainty in D squared and the percentage uncertainty in T. So this is equal to the percentage uncertainty in M plus the percentage uncertainty in D squared plus the percentage uncertainty in the thickness. And then we have to expand the percentage uncertainty in D squared is 2 times the percentage uncertainty in the thickness plus the percentage uncertainty in the diameter plus the percentage uncertainty in the thickness, and therefore 1.18% plus 2 times 1.92% plus 5.26%. So this is 10.28% or about 10.3%. And again, I have a video that I thoroughly go over how to calculate uncertainties and percentage uncertainties and so on. If I forget to put it in the link, if I forget to put the link in the description of this video, ask me in the comments and I'm gonna point you towards the video, or you can search for the video yourselves in my channel. So let's move on to question number 8, and I'm gonna take a sip of water. All right. An object moving through a fluid experiences a drag force due to the viscosity of the fluid. Question A. Some liquid chocolate is poured into a mold. Within the chocolate, a bubble of air is formed. The bubble has negligible weight and moves upwards at a constant speed as shown. Calculate the constant speed at which the air bubble moves upwards in the liquid chocolate. And they give you the radius of the air bubble, the density of liquid chocolate, and the viscosity of liquid chocolate. So we have a free body diagram pretty much, okay? And they tell us that we move upwards. So first of all, let's calculate the drag force. So the drag, not calculate, we're just gonna write it down for now, okay? This is equal to the Stokes force, which is equal to 6 pi times the viscosity eta times the radius of the bubble in this case times the velocity, okay? The upthrust in this case is equal to the displaced volume of liquid, okay? So it's equal to the weight of the displaced volume. What's the displaced volume? The density of the chocolate times G times the volume of the bubble, which is 4/3 pi r cubed. Okay, now what's going on here? The upthrust minus the drag are equal to mass times acceleration, but in this case we don't have acceleration, we have a constant speed, right? So this tells us that the upthrust is equal to the drag. Okay, so we can make these two guys equal to each other. So we have the density of the chocolate times G times the volume of the bubble, which is a sphere, is equal to 6 pi times the viscosity times r times the velocity, and that's terminal velocity. This is what it means to have a constant speed. Okay, so pi cancels, one of the radii cancels. We can also reduce this to a 3 and that to a 2, and we have to solve for the velocity. So the velocity is 2 times the density of the chocolate times G times r squared over 9 times the viscosity. And now we can plug in numbers. 2 over 9 times 925, and we have kilograms per cubic meters. By the way, when I work out, when I plug in numbers into formulas, I put all the numbers to the left and all the units to the right, okay? So, and then we have times 9.81, which is G, and this is meters per second squared. What else do we have? Times the radius squared, so 6.8 times 10 to the negative 3 squared, and then we have meters squared. Okay, and then in the denominator we have just 52.6 pascals seconds. Okay, so these cancel, and let's carry the calculation. We find 1.77 times 10 to the negative 3, and then we have kilograms per pascals seconds cubed, which works out to meters per second, and I'm going to show you how, okay, because I think these kind of things are useful. So this is equal to kilograms, and then pascals is in newtons over meters squared, and then we have seconds cubed, and then we have to recall that 1 newton is 1 kilogram times meters over second squared, because F is equal ma. So kilograms meters squared, and then the newton is kilograms times meters over second squared, and then over seconds cubed. So beautiful. This works out to be meters per second, and we can write our final value. Velocity is about 1.8 times 10 to the negative 3 meters per second, and this is the terminal velocity of the bubble. Okay, this was another like a long problem. Okay, so but I guess they have, I don't know, they want to test various things in this paper 3, which it was nevertheless really interesting working on this paper. So you guys took me like I don't know, I don't want to say, but a few thousand of years back when I was taking exams in order to enter universities or get degrees and stuff like that. So anyway, so part B. The viscosity of a gas increases with temperature. It is suggested that the relationship between viscosity and temperature T is of the form eta equals A T to the B, where A and B are constants. Explain why a graph of log of eta against log of T will give a straight line. Okay, if we take the log of both sides, we will have a log of eta is a log of A times T to the B. So this works out to be log of eta is equal to B log of T plus log of A, which is of the form y equals mx plus c, which is a straight line. So let me use a clean page. So straight line with m equal to the gradient equal to, what was it, b, and c is log a is the y intercept. Okay. Part 2, the table shows data for the viscosity of hydrogen gas over a range of temperatures. Okay. Plot a graph of log of eta against log of T. You should use the columns provided to show any process data, and the process data will be log of T and then log of, I'm sorry, I made a mistake, log of eta, and this is in units of, sorry, actually, yeah, I was correct. I'm sorry. Log of eta over millipascals times seconds. Now is the time where I will pause the video, and when I am back, you will see the final results. Okay. All right. So these are the results. Plot a graph of log of eta against log of T. You should use the columns provided. Okay. We said that before. One small trick I want to show you when you work with data like this. So the range of log of T, so log of T is in the range of 2.09 to 2.24, which we can sorry, to 2.67, I'm sorry, 67. So we can cover this range using 2, 2.1, 2.2, 2.3, etc. I mean, for the marking of the graph, and this is the plotting area they give us. And now for log of eta, the range is from 0.66 to 108. So we can mark our plot using 0.6, 0.7, 0.8, and so on. Okay, so let me start this, and at some point I'm gonna speed up the video for you to see the final result. So this is the y-axis, and this is the x-axis. Okay, so here we have log of t, and here we have log of eta. Okay, so we'll start log of t with 2, and then 2.1, 2.2, 2.3, 2.4. What was the range again? Up to 2.7. Okay, 2.5, 2.6, and this last one is 2.7, and then 0.6, 0.7, 0.8, 0.9, 1, 1.1. By the way, this is slightly wrong. Okay, is that enough? We cover everything? Yes. Okay, and let's put the first data point in, and then I will speed the video. So the first pair is 0.66 and 2.09. So this is let me think, 0.66 is over here, and 2.09 is this point. Okay, maybe I should use green. So 0.66 and 2.09 is that point over there. Okay, now I'm gonna speed up the video. All right, so all the data points are in, and let's draw a line of best fit. So it should pass through as many points as possible. So that's good. And conveniently, the y-intercept is 0.6, so that's good. Okay, so this is a nice plot, I think. So let's see. Okay, part 3, determine values for a and b. You are not required to state the units of a. Okay, let's start with b, actually, which can be calculated from the gradient. So b is equal to the gradient, which is equal to, we can take, I'm gonna use blue. So we can take these points and this point. I mean, we can take the whole graph pretty much. So we can use 1.1 minus 0.6 over 2.7. So this over that, 2.7 minus 2, and I will need to use my calculator. So 1.1 minus 0.6 over 0.7 pretty much yields 0.71. Okay, 0.71. Do we need to provide units? No. Okay, I mean, I have the mark scheme in front of me. They say that b should be between 0.68 and 0.75. We found 0.71, so it's good. Okay, and then a can be calculated from the y-intercept, since pretty much 0.6 will be equal to log of a. Therefore, a is 10 to the 0.6, right? So that gives me 3.98 which disagrees with the mark scheme. In the mark scheme, they say that A is 0.15, pretty much, 0.148. I don't know why. I think it's a typo, or maybe maybe I have something wrong in my reasoning. But yeah, let's keep it, and let me know in the comments, guys. I don't know. Anyway, I don't see anything wrong in the way I calculated it, but let me know in the comments. So maybe the mark scheme made a mistake. So I can't really figure out why they have that value. So let's move on to question 9. A cantilever is a beam fixed at one end. A student made a cantilever by clamping a meter rule to a bench and attached a mass M at the free end as shown. The student displaced the free end through a small distance. When the free end was released, the cantilever oscillated with simple harmonic motion of period t. A, the student measured the time for 5 oscillations with an electronic stopwatch. This was repeated twice. I, explain one modification to the apparatus which would improve the accuracy of the data the student obtained. So we can use a fixed mark, so maybe here, okay, so you can figure out where the oscillation stops and starts again. So used a fixed marker placed at the equilibrium position yeah, just the equilibrium position. So this would be the equilibrium position. Actually no, let me think. So since we have a mass there, the equilibrium position will be here, okay, because it's gonna oscillate back and forth like that. So the marker should be placed there. Okay. All right. And we can time the oscillations. The other thing we can improve, but they ask for one, but okay. Time the oscillations when the end passes the marker. And this reduces timing uncertainty. Okay, part 2. Explain one modification to the student's method which would reduce the percentage uncertainty in her measurement of t. The percentage uncertainty in the period is equal to the absolute uncertainty of the period over t times 100%. So if we measure for a larger number of oscillations, okay, and if we measure for a larger number of oscillations, we would increase t and hence reduce the percentage uncertainty in t. All right, part B. The length of the meter rule overhanging the bench was L. The period of oscillation T is related to Lm and the Young modulus E of the wood of the meter rule by the expression T squared proportional to mL cubed over the Young's modulus. The student repeated the timing measurements for a half meter rule. The half meter rule had the same added mass m, width, and thickness as the meter rule. The meter rule was made from wood of Young modulus E1, and the half meter rule was made from wood of Young modulus E2. The student collected the following data. So we see the Young modulus, the length, and the time for 5 oscillations in 3 different occasions. And the table below gives the Young modulus values of various types of wood. All right. Deduce the type of wood each rule is made from. Okay, so this looks tricky, but let's start by calculating, first of all, the T1 average. This is going to be 14.69 plus 14.64 plus 14.76 over 3, which is equal to 14.70 seconds. So T1 is going to be equal to T1 average over 5, or 2.94 seconds. So similarly, T2 is 5.33 plus 5.4 plus 5.24 over 3. This yields 5.32 seconds, or the average period is T2 over 5, which is 106 seconds. Okay, now the tricky part. They don't give us an equality, they give us a proportionality. Okay, so when we divide two quantities that are proportional to each other, we can use an equality. So what I'm trying to say is that we need a clean page first of all. So T1 squared is proportional to ML1 cubed over the Young's modulus, and T2 prime squared is proportional to ML2 cubed over E2. But if we divide these two, T1 squared over T2 squared, we are gonna uncover an equality, and this is because the thickness and cross-sectional area of the two woods are the same. Therefore, this is an equality, so we can write this as ML1 cubed over E1 over ML2 cubed over E2. M cancels, and this is equal to E2 over E1 times L1 cubed over L2 cubed. Therefore, E1 over E2 is going to be equal to T2 squared times L1 cubed over T1 squared times L2 cubed, which is equal to 106 squared times 0.95 cubed over 2.94 squared times 0.45 cubed, and this is equal to 1.22. Okay, so this ratio is 1.22, and if we go to this table and we divide E of spruce over E of cedar, we find 1.25. You should also divide spruce with pine. Sorry, since what we found, our result is larger than 1, right? 1.22. Then you have to divide pine by spruce, pine by cedar, and then spruce by cedar. Okay, and if you do that, you will see that the closest to the value we found, to the ratio we found, is spruce and cedar. So we can conclude, so this is E of spruce over E of cedar. So the first wood is spruce and the second wood is cedar. And this is what they are asking, right? Deduce the type of wood. So we deduced it. So we are done here. Okay, so this is spruce and the second wood is cedar. All right, this was an interesting problem. Let's move on though to question 10. The potential difference, PD, from a power pack alternates at a frequency of 50 Hz. The root mean square value of the output potential difference is measured to be 8.5 volts using an AC voltmeter. The output from the power pack is connected to a resistor of resistance 1.5 ohms. Show that the rate of power dissipation in the resistor is about 48 watts. Okay, so the power is simply V squared over R. So 1.5 squared over 1.5 yields 48.2 watts, which is about 48 watts. Okay, good start. Part B. A lab technician used the resistor to heat 1.25 times 10 to the negative 4 cubic meters of milk in a beaker. Calculate the time taken for the milk to increase in temperature by 12 degrees Celsius. The specific heat capacity of milk is 3,930 joules per kilogram per Kelvin, and the density of milk is 1,050 kilograms per cubic meters. Okay, so power is energy per time, but we want to calculate time, so time is energy over power, and energy is C times M times delta theta over the power. One detail here, delta theta in Celsius is equal to delta theta in Kelvin, okay? And this is because to convert from Celsius to Kelvin, we have to subtract the temperature from 273. So if we take a temperature difference, that factor of 273 gets cancelled, right? So we don't have to worry about that. So we have C, which is we're not given the mass, we're given the volume. So this is equal to C times the density times the volume, because mass is density times volume, times delta theta over the power. And now it's time to plug in numbers. So 3,930 times 1,050 times 1.25 times 10 to the negative 4 times 12 over 48.2, which we calculated earlier, and this yields 128.42 seconds, which is about 128.4 seconds. So about 2 minutes, in other words. Okay. C. This awards 6 marks. Okay, so let's read it. The lab technician used an oscilloscope to determine the supply frequency and check the RMS output PD displayed by the voltmeter. Describe the methods the technician should use. Okay, first of all, the oscilloscope, let me use a clean page, looks something like this. It's a screen. And by the way, the first video games, I believe, were created by people who used oscilloscopes back in the 50s and 60s in the Cold War era. So they were playing with the dot displayed, and they were trying to make it jump or do things. So, but anyway, it looks something like this. So your time is going to be here and your voltage here, okay? And you will have little squares. So it will look like this, I guess. Sorry for the really crude sketch here, but this is the time base, so time base, and this over here is going to be the voltage sensitivity. And you can adjust those in a fashion that will allow you to show the wave. So the wave will look something like this, okay? So you have to adjust the time so that you will be able to see the voltage and be able to calculate the period, which is from one peak to another peak, okay? It's always a fun game to show to students how you can just plug in current from the plug and calculate things. So anyway, so first step, connect oscilloscope to AC supply. Okay, adjust time, adjust the time base, okay, so that one complete wave or several waves are visible in the screen. Okay. Measure the horizontal distance from peak to peak. Okay. Multiply distance by the time to find the period, and I mean this distance. So for example, here we see 1, 2, about 3.5 boxes. So you multiply the 3.5 boxes by the time base for one box to find the period. Okay, so this is what I mean. So if you find t, the frequency is simply 1 over t, right? And then use the voltage sensitivity, okay, and vertical amplitude to find V naught. And then VRMS is simply V naught over the square root of 2. So compare F and VRMS with given. Okay, and this is a complete experimental process, I guess, to calculate the required quantities. All right, moving on to question 11. Particle accelerators produce beams of high-speed charged particles, which are used to investigate particle collisions. New particles are created during the collisions. In the Large Hadron Collider, LHC, protons are maintained in a circular path by the force exerted on the protons due to a magnetic field. The magnetic flux density required to maintain the protons in the circular path increases as the kinetic energy of the protons increases. Explain why. Okay, so in these types of accelerators, we have the force QVB acting as the centripetal force mv squared over r to keep these particles in a circular orbit. V cancels, so the radius is equal to mv over qb. mv is simply the momentum p over qb, and then recall that the kinetic energy is p squared over 2m, which means that p is the square root of 2m times the kinetic energy. So I'm gonna go to a clean page again. This is not the clean page I wanted, but okay, it works. So the radius is equal to 2 times mass times the kinetic energy over q times b. So if the kinetic energy increases, comma, in order to keep r fixed, since the LHC is a fixed ring, right, of fixed radius. So to keep r fixed, we must increase b. Okay, and that's the answer. Question 2. Calculate the magnetic flux density required to maintain the protons in the LHC when the protons are traveling at a speed of 3 times 10 to the 7 meters per second. Okay, so for this we're gonna use we're gonna take this equation and take advantage of it. So we will solve for B is m times v over r times q times e, pretty much, since the charge of a proton is simply e, the charge of one electron, but positive. Did I mess something up? No. Okay, they give us the circumference of LHC, so c is 2 pi r, so r is c over 2 pi, or 4,299.4 meters. So if we plug in for B, and let me put an asterisk. So we are moving here. So B is, let me think, 1.67 times 10 to the negative 27 is the mass of the proton, times the speed, which is 3 times 10 to the 7 meters per second, over the charge of the electron, which is 1.6 times 10 to the negative 19, times the radius, which is 4,299.4, yields 7.28 times 10 to the negative 5 Teslas. Okay, so not too bad. Actually, it's a small magnetic field. I was kind of surprised a little bit. So, part 3, a maximum of 13,600 GeV of energy is available to create a new particle. You can also write that as 13.6, 13.6 TeV is the same as that. But anyway, okay, calculate theoretical maximum mass in kilograms, of the new particle. All right, so good old Einstein, mc squared. So m is equal to the energy over c squared. The energy is 13,600 times 10 to the 9 EVs, and then 1 EV is 1.6 times 10 to the negative 19, and then c squared is 3 times 10 to the 8 squared. Okay, this yields, let me write it here actually, there is space, 2.42 times 10 to the negative 23 kilograms. Okay, another long writing problem. B. 50 years ago, fixed target collision experiments were carried out at the Stanford Linear Accelerator Center. It's a world famous center in California at Stanford University. It's commonly known as SLAC. I've never been, sadly, because I've never been to California, even though I lived in the US for 10 years. So anyway, maybe in the future. In these experiments, high-speed particles were made to collide with a stationary target. Currently, colliding beam experiments are carried out at SLAC. In these experiments, high-speed particles traveling in opposite directions are made to collide head-on. For a given total energy in the collision, colliding beam experiments allow particles to be created with a larger mass than could be created in a fixed target experiment. Explain why colliding beam experiments allow a new particle with a larger mass to be created. You should consider how the conservation of energy and the conservation of momentum apply to each type of collision. Okay, so in a fixed target experiment, okay, momentum must be conserved, okay, after the collision. So the new particle must have some momentum, okay. Not all energy can go into creating mass, since we have to conserve energy and mass. Therefore, the kinetic energy before plus mc squared before must be equal to m nu, the new particle's mass, c squared, times the kinetic energy of the new particle, because the new particle has to carry some momentum to conserve momentum, and we also need to conserve energy. Okay, so only a part of the initial energy becomes mass. And this is the scenario in which we have a fixed target, okay? Now let's go see, let's use square paper, okay? So let's go see now what happens when we have a head-on collision experiment. So in a head-on collision experiment, let me read one more time. High speed, okay. Okay, so in a head-on experiment with equal and opposite momenta, it doesn't have to be like that, but just to explain. So in a head-on collision experiment with equal and opposite momenta, the total momentum before is 0. Thus, it has to be 0 after the collision. All right. So the produced particle, or particles, okay, doesn't need a leftover kinetic energy, and almost all energy can go into mass. And the conservation of mass energy is given by 2 times mc squared, assuming that we are colliding the same particles, say 2 beams of protons, okay, plus 2 times the kinetic energy of these guys, can all go into creating a new particle c squared, okay? So this is amazing, actually. It gives you a lot of energy. So colliding beams can create massive particles. And that's a possible answer, guys. All right. And number 12 is the last question. And this is a question that in the international A levels, it will appear actually at the AS level in unit 3. Okay, so students that are year 12. So in an experiment to determine the acceleration of free fall g, a metal cylinder was dropped from rest down a glass tube. A light gate was positioned close to the outside of the glass tube as shown. The light gate was connected to a data logger that recorded the time taken for the cylinder to pass the gate. A student recorded the following data: T1, T2, T3, and T4. The student omitted T1 when calculating the mean time. He justified this by stating that T1 is an anomalous result. Another student stated that the correct mean time should use all the data in the table. Explain who is correct. So 7.85 seconds. Let me write it again. 7.85 seconds is not very different. From the rest of the values. Okay. So it must be included. Or the second student is correct. Okay. All right. I mean, to exclude it, it should be something like 7.5 milliseconds. Okay. I mean, these values are really close to each other. All right. 2. Calculate the percentage uncertainty in the mean time, T mean. Okay. So first of all, let's calculate T mean. That's 7.79 plus 7.81 plus 7.8 plus 7.85 over 4 gives 7.81 milliseconds. And again, I need a clean page. The absolute uncertainty in these measurements of t is equal to the half range. And to calculate the half range, we find the most extreme values, so 7.85 and 7.79, and subtract them and divide by 2. 7.85 minus 7.79 over 2. This yields 0.03 milliseconds, and we can now calculate the percentage uncertainty in the time, which is equal to the absolute uncertainty in the time over the time times 100, so 0.03 over 7.81 times 100, and this is simply 0.38%, or we can write it as 0.4%. Okay, the student used the mean time to calculate the velocity of the metal cylinder as it moved past the light gate. State the extra measurement the student must have made to calculate this velocity. So I guess they mean the height of the cylinder, because you can use v squared is u squared plus 2as, and the s is the height. So height of cylinder. Right, B. The metal cylinder fell through a distance of 0.75 meters before reaching the light gate. Wait, I made a mistake. Can I correct the mistake? Let me think. Something bothers me in the answer I just gave you with the height. Okay. This is a mistake, guys. So I can edit it out, but I'm gonna leave it because I want you to see that teachers and physicists and even PhDs make mistakes. So they say that the student used the mean time to calculate the velocity of the metal cylinder as it moved past the light gate. State the extra measurement the student must have made to calculate this velocity. So the height of the cylinder, will help you calculate V is h over the time. So this is the time needed to pass from the light gate. So to calculate the velocity, you need the height of the cylinder, because it goes through the light gate. Okay, in other words, so this guy falls like this. Okay, so it passes through the light gate, so we need to know its height, since we know the time needed to pass through the light gate, right? To calculate the velocity is height over time. Okay, I'm sorry about that. Let's move to part B. The metal cylinder fell through a distance of 0.75 meters before reaching the light gate. Calculate the velocity of the metal cylinder as it reached the light gate. So, okay, now we use the Suvat equations. So, v squared is u squared plus 2as. So in this case, we have v squared is 2 times g times s, the height. So we can take the square root of that to calculate the velocity. The initial speed is 0. So the square root of 2 times 9.81 times 0.75 yields 3.84 meters per second. We can write it as 3.8 meters per second. And the last one, 3, explain why a light gate and data logger were used in this experiment rather than a stopwatch. You should refer to your answer to be 1. So, okay. So the cylinder travels quickly. Okay. I mean, yeah, it travels quickly. Time is too short. So time is about 0.01 seconds. So using a stopwatch to time that will be really, really hard. So using a data logger reduces the reaction time. Okay, and this was paper 3, guys, from 2025, the most recent one. Okay, now the plan is, since I started this series with the UK past papers, okay, I also plan to go over the AES Core Physics 1 and AES Core Physics 2 of the AES curriculum, okay, so that you have a complete 2025 past papers series from the UK. I'm going to try to do the same with the international test. This takes time, so I cannot really upload a video per day. This was the plan back when I started this YouTube channel, and then at some point I realized this is too much, because I really need to go through the papers and give you my own interpretations and solutions. I hope these videos are useful. Thank you to those who comment in the videos. Please like these videos, promote them, I don't know, spread the word or something like that. And if you have questions, let me know in the comments. See you in the next one, guys. Bye.